turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists podcast, the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith, and today, in partnership with UK Research and Innovation, we're exploring attempts to forecast and prevent flooding. Each year, floods affect more people worldwide than any other natural hazard, affecting homes, national and local infrastructure, and the environment. So today, we're going to examine what flooding is, why it happens, and what can be done to better manage it. Later on, we'll be finding out why flooding is so dangerous and how computers can help to forecast these extreme weather events and their impacts. But first, beginning with the basics of the various forms flooding can take, including the contributions of storm surges from the sea, here's the former Met Office and BBC weather forecaster, Peter Gibbs.
They're almost always weather driven, unless it's something like a burst water main or something like that. But they're pretty much always due to an excess of rainfall. But we break flooding down into three kind of broad types. So it's fluvial, pluvial, and coastal. So fluvial just means basically rivers spreading outside their normal boundaries. So, rivers are fed by catchments, big areas that collect rainfall. And if you've got a big Atlantic weather system coming in, putting a lot of rainfall into a catchment, it's got to flow down through the river and out to the sea. And if there's too much rain for the river to cope with, that's when you actually get the flooding. It extends out into its floodplain. It's a natural process, but it can still be very disruptive. It's got a little bit more to it, though, in terms of complexity, because the shape and size of the catchment can make a big difference in terms of the flooding risk. For example, I grew up in Kendal, just on the south side of the Lake District, on the River Kent. Now, that drops from the southern Lake District hills at 2,000 feet to Morecambe Bay in a space of just 20 miles. So if you get heavy rain up in the hills, whoosh, sudden flood, space of a few hours, and then it's gone. Something like the Severn or the River Ouse, huge catchment areas, gentler slopes. So rain that falls in the Welsh Hills, for example, can take several days to get down to bigger towns and cities further downriver, and then last for several days because it can't actually flow away. Pluvial flooding, that's basically what we know as flash flooding. Say a passing thunderstorm deposits a huge amount of rain in a short space of time over a fairly small area. We've all had that experience, haven't we, Chris, of, driving along in the car, sudden downpour, and then you come out the other side and it's bone dry again. So these are really difficult things to pin down from a forecasting point of view. If it falls in a place like an urban, steep valley, then potentially you've got a difficult situation. If it's falling on a flat rural landscape, much less so. And then you mentioned storm surges. Well, that's where the worst coastal flooding comes from. Big storm combined with high spring tides, that can overwhelm coastal defences. The worst one of those in the UK was the North Sea flood of 31st of January 1953. A wall of water swept down the east coast of England into Belgium, the Netherlands. No warning, on a dark winter's night, over 2,500 people lost their lives. So these can be really big, really serious events.
You've mentioned a lot of kind of natural features that tend to influence things. The steepness of the river catchment, the extent of the river catchment, but also we as humans inhabiting the land are making a massive difference, I would think, because if we come along and we turn what would have been, say, natural land into a concreted over town, then that becomes impervious.
Yeah, in urban areas, impervious surfaces are certainly a big issue, particularly as rain is getting heavier due to climate change. In the bigger catchments, increasingly it's recognised that things like deforestation, peat bogs being degraded reduces the capacity of those catchments to actually soak up a lot of the rain when it initially falls, to just slow down that release into the river system. So there is quite a push to go back towards sort of nature-based solutions as a way of perhaps trying to mitigate the flooding issue in the future.
Is there evidence that the frequency of flooding is changing with things like climate change?
There's pretty good evidence, actually. You might remember the horrendously wet autumn and winter of 2023-24, where it just did not want to stop raining, just one weather system after another sweeping in from the Atlantic. So the Met Office, following that, did an analysis and looking at just how exceptional that rainfall was. They found in a pre-industrial climate, the sort of rain we saw through that autumn winter would have had a return period of about 1 in 50 years. In today's climate, though, it's more like 1 in 5. That's an extraordinary change. A lot of this is down to the fact that a warmer atmosphere holds more moisture. For every 1 degree Celsius you raise the temperature of the air, it can hold 7% more moisture. So a warmer climate, it doesn't necessarily rain more often, but when it does rain, it rains heavier.
Are there any tangible, tractable examples of how this is affecting everyone?
Well, I've got a couple. I mean, the Thames Barrier, which actually was constructed as a response to that horrendous North Sea flood back in 1953. In its early years of operation, in the 1980s, for example, it closed just 4 times. In the 2010s, it closed 74 times. And it's not just to prevent big tides coming up the river. Half of the closures now are to deal with the amount of water coming down the river in floods, because if you have that water coming down and then you get even a normal tide coming back up the river, it backs up and it floods upstream. So it's having to deal with stuff way above the original design spec. And another example from the River Severn. Now, it's always been prone to flooding. Everybody that lives along the River Severn expects flooding sometimes. But Worcestershire County Cricket Club, which has been at its Riverside Ground at New Road in Worcester since 1865, is actively looking to move, as having experienced just 5 major floods in the first 135 years of its existence. It's been going underwater several times each winter in recent years. So, a pretty clear example there that things are getting worse.
That's not cricket, is it?
It's certainly not, no.
Weather forecaster Peter Gibbs there. Well, now to the National Oceanography Centre. As Peter was just saying, rainfall is only part of the flooding equation. High sea levels, which can arise through the combined effects of tides and also low air pressure, also play a major role. They can inundate low-lying coastal terrain directly, and they can also push water back up rivers and estuaries, leading to knock-on flooding inland as well. The team at the National Oceanography Centre track and try to anticipate these effects using tools like tide gauges around the coast to measure sea levels directly, coupled with satellite images that can log ocean heights from space. These measures can all be integrated with local weather forecasts to try to predict storm surges and give early warnings that can help communities to prepare for the worst. This is what scientist Joanne Williams spends her days doing.
There's 2 big effects from the weather on tides. One is from the wind, which literally pushes water into different places in the ocean. And the other is from the air pressure. When the air pressure is high, you get pushing down of that area of ocean. And when you get low pressure, like you get with a storm, the ocean is able to rise up into that area. And that increases the water level there.
And when you're making the monitoring, yes, we've got satellites in space that give you a sort of bird's eye view. On the ground, though, there are tide gauges. How do they work, and how do you get the data from those? And how good is the resolution of that?
So satellites are fantastic for giving you a big spatial picture. They can see a lot of area, but they only see it very occasionally when the satellite passes over. The tide gauges, there's only a few of them around the coast. There's about 40 major tide gauges in the UK, but they sit there measuring every day continuously. So we get a piece of data back from them, usually about every 15 minutes. And they're measuring what happens right in that harbour or up that river where people are actually needing the information as well, whereas the satellites tend to measure out at sea, a little bit further away from the coast.
So once those data land on your desk, you've got the incidental data from the satellite when it passes over, giving you the bird's eye view bits of the ocean. You've got the day-to-day data coming in from those tide gauges. How do you use that, though?
What we're looking for is the difference between what's predicted from long-term astronomical predictions of tides, things that are very regular tides that happen because of the position of the moon, and the difference between that and what's going on due to the weather. The differences between those signals tell us what effect the weather is having over that day. And if that's deviating from our forecasts, then we need to know why that's deviating.
And do you aim to build a sort of big picture model of this then, so that if in the future we see a similar pattern of changes, we can make predictions and warn people earlier? Is that the point of this?
Yes, so there is regular modelling of the storm surges. So every day the Met Office weather forecast is run, and then from that weather model, computer model, that information then feeds into an ocean model, which is a grid of boxes about 7 kilometres each box size across the UK. And then in each box, you say, well, what's the sea level going to be in that space? And that model is run several times a day due to the weather forecast. And then what we're looking to do is to gradually make improvements to that model, see if there are areas where it's not working as it should do, and also how it's likely to change in the future as climate change changes how tides and sea level are around the coast.
You'll get, therefore, a snapshot of what we think the sea is going to be doing, but there's going to be things going on land, obviously, because there could be rain falling on the land, there could be water coming down a river anyway. So how do you integrate what's going on over the land and then reaching the sea with what the sea is doing? Because presumably it is the interaction of all of those effects together with what the weather is also doing to sea level that's going to make a difference whether or not there is a flood.
Yeah, and that's one of the most difficult areas of research at the moment, because there's been historically a lot of work out at sea, and there's been other work which has been very much upriver, and the two fields have historically not met in the middle. So that's where there's a lot of interest at the moment about, we call it compound flooding, when you get the effects of rainfall and rivers and groundwater as well, and at the same time as a really high tide and storm surges coming in from the sea. So that's a really interesting area for research at the moment.
I don't want to cost you your job, Jo, but are you any good? I don't mean you personally, as in it's almost the royal we of weather, but when you come up with, and models like this come up with the answers that they do, how often are you hitting the nail on the head and getting it right? And when you do get it wrong, how wrong does it go and why?
Yeah, the surge models for the out at sea are really quite good. I mean, we're right within about 10 centimetres nearly all the time. The problems with it are about trying to forecast further in advance. So ideally, you want to know what the surge is going to be several days in advance, so you can make plans to close flood barriers, put in temporary defences, evacuate if necessary. So you want as much notice on that as possible. And that's all about improving that forecast, the weather point of view, and also looking at they call it an ensemble of forecasts, where they run several different versions to say, what could happen is it could go one way, the storm could go the other way, which of those is more likely? And, if it goes into a severe one, then, what do we need to do? So that's a big area of research at the moment as well, is looking into those ensembles and the best way to run those.
Joanne Williams at the National Oceanography Centre there.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientists podcast with me, Chris Smith, and today, in partnership with UK Research and Innovation, we're examining flooding and what the UK is trying to do about it. Now, we're going to look with slightly more fine-grained detail at the mechanics of flooding and what aspects of what we're doing to the environment can make things better and worse. Hannah Cloke is a leading expert in flood hydrology at the University of Reading.
There are lots of risks associated with flooding. It's not just the water, it is the contamination, it is people not being ready for the dangers posed from open manholes, as well as being swept away in swollen rivers.
What actually turns a bit of excess water into a flood and a jeopardy?
Well, it's not just about the rain, it's about what happens to the rain when it hits the ground. And often we have built over our landscape, we've concreted over the whole place. And so that water runs off really very quickly and can overwhelm drainage systems. And that type of flooding can happen really quickly. So it might just be a puddle one moment and then it suddenly switches into a dangerous flood. Also, we have lots of rivers where we have straightened those rivers, we've constrained them. And that's really dangerous too, because they suddenly overtop those levees at the side of the river that we've built, often kind of concrete structures. And then we built on the floodplain. So we're living on the floodplain in those dangerous places. So we've got people in the way of the floodwater. And that's the big problem.
When water has to go from land out to sea, what affects how quickly it can do that? And what's the most optimal solution? Is it to have massive rivers that are really deep, unobstructed, and they can flow really fast? Or is it to keep the water on the land and let it trickle more gently into whatever waterways we've got and make its way gently out to sea?
If we engineer our rivers and make them deeper and wider and bigger, that can carry the water away quicker. That's true, that actually does happen, but it can mean that we have really quite violent, huge rivers that are moving very, very fast and that are difficult to control. And when we get a very big flood come along, that means that those rivers can flood very violently indeed. It's much better to try and hold on to that rain wherever it falls across the landscape. Soil is a really good bucket for catching rain, so we need to make sure that our soil can soak up that rain across our landscape. And where we have built our cities, where we have concreted over everything and built roads, we need to therefore put extra ways of catching that rain back into the landscape. So green roofs and rain gardens and things like that, wherever we can, to try and hold on to that water, to slow it down, to stop it rushing down to the river and overwhelming towns downstream.
I went to a new development yesterday for work, and I noticed that they've built a big area that looks like a garden, but it's got an almost dry pond in it. Is that part of this sort of infrastructure you're referring to? It's creating places where water can gather if it has to slow things down.
Yes, and these are exactly the kinds of things I'm talking about. They look often like a garden or sometimes just like a random piece of land that looks like it's just been left. But they're super important to hold on to that rain. They're sustainable drainage systems, and they're a really important part of new developments, but we need more of them.
Suppose there must be a tension because the developers want to pack as much into that space because the land is precious, and the hydrologists like you want as many of those sorts of open areas that are soakaways as you can get to avoid floods.
Yes, there's always this tension between, developers and hydrologists especially, because developers also like to build on the floodplain, which is also very dangerous. But yes, having this space for the water to catch the rain or to indeed hold on to floodwater when the rivers do flood, it's so important. But the pressure to build houses across our country, the local authorities are really struggling to find the land to build the houses that they need to build. And so it is a massive tension.
Has this and the involvement of hydrologists gone up the agenda in recent years? It seems like it's something we hear, probably for a good reason, a lot more about now than historically.
I think there is a recognition that you really need to understand where the water is going and how to look after our landscape as well, to look after our cities, to look after the people, to be able to predict in advance where those floods might occur, and also help people understand what they need to do in order to keep themselves and their families safe. There's a lot of different aspects of hydrology. Being able to understand what future rainfall is going to look like is one part of it, but then knowing how that water moves through the landscape and being able to predict really extreme events ahead of time, that's super important.
Do we have a risk map for a country like the UK where we think, well, those are the hotspots for flooding, at least at the moment? These are areas that with climate change might become a hotspot. These are areas where we need to have special measures to make sure we've anticipated the threat and we've used all of the things available to us to try to mitigate.
I think it's really important to understand that the whole of the UK is at risk of flooding. Some of that's because of pluvial flooding, so flooding that comes from just heavy rainfall. This is one of the things that we know is changing rapidly because of climate change. And of course, we've built over the landscape, so we're more vulnerable to that type of flooding. And people don't really know how to behave in this type of flooding. So that can happen anywhere. That's really important. The whole of the country is not adequately prepared for these types of very fast flash flood. Also, of course, people who live on the floodplain, we have a lot of properties on the floodplain already. All of those people are living in danger. Those risk maps are very well crafted now, so we have a good understanding of people who are at risk. And we have early warning systems and other things that we can do to evacuate people if we have this early indication that those floods are going to happen.
What about the change in weather generally, though? We're getting a pattern now where we tend to have long, dry spells. And people argue what this does is it really bakes the ground hard. So when the rain does come down, because the ground isn't receptive to water, because it's so hard and impervious, the water just runs off. And in fact, flooding is becoming more likely now, even though we might have not much more rain coming down.
Actually, as the climate is changing, these long dry spells and these risks from particularly flash flooding are going to get worse. So it's something we're going to have to deal with. And if we could just hold on to that water a bit better that we get in the floods, then we could keep it for when we need it in the droughts. So we need to do much more around holding on to that water and making sure that we have it.
Hannah Cloak there at the University of Reading. And finally this week, we're going to be exploring how AI and computer modelling can help scientists to tackle flooding. Nicoletta Leonardi is a professor of coastal dynamics at the University of Liverpool. Her work focuses on combining computing, remote sensing and environmental modelling to better understand coastal flooding and the likely effectiveness of different interventions that we can make.
There are different types of models, which means that we have programmed equations into the computers. And those equations can tell us how water moves and can also tell us how sediment moves. And based on those movements, maybe we have some areas where we have a bit of erosion and areas where we have a bit of accretion. And when we have a storm, we can predict the water levels that are going to happen.
And presumably, if you're able to make those sorts of judgments, you can also make predictions about the future, because you can say, well, as the climate changes and the sea level changes and the coastline changes, these are the likely consequences. You can sort of run the simulation forward.
Yes, that's correct. That's one reason we use models. We can simulate and scenarios which haven't happened yet. So, for instance, we could add a component of sea level rise and see what that does to the coastline or to the propagation of storms.
Are these models any good? So, in other words, if you run them and then say, what would be the outcome between this year and this year, using data where we know the outcome, and you compare what the model thought would happen, are they pretty accurate?
They can be pretty accurate, yes. And most of the time we do use an ensemble approach, which means that we actually don't just run one simulation, but we do run a lot of simulations for the same scenario by changing a bit the internal parameter of the model. So they're pretty accurate, I'd say, at the moment.
Can you almost run them in reverse? And what I'm getting at is, can you ask the model, what would I have to do to not end up with a particular outcome, a flood or inundation of a particular patch of coastline, so that we can begin to work out ways we might be able to mitigate the effects of things like climate change, the things like sea level rise, the things like erosion?
Yes, absolutely. And actually, we do that all the time. For instance, when we want to evaluate the impact of different coastal management interventions, whether, hard coastal engineering, such as seawalls, or more nature-based solutions, such as seagrasses or salt marsh restoration, we can run the model by adding different management, which actually are not existent, to see what's their impact on, let's say, water level propagations and storm energy dissipation.
Most people, when you talk about coastal defences, do immediately think about building very big, very expensive, tough to maintain defences. But you're beginning to say things like salt marshes and seagrasses. Are they actually effective?
Yes, I think there is growing evidence that those measures can be effective. And there are various ways they can be effective. For once, they can create a physical barrier in between the sea and assets that we want to protect. If, for instance, we think about restoring a salt marsh, they can dissipate energy because those surfaces usually have a vegetation on top, and vegetation creates a roughness that can help to dissipate wave and water levels. And finally, they support the long-term resilience of coastal landscape because they can also help to trap sediments.
Have you actually tested this? Have you put things like seagrasses into the models you're creating to see if they will make those sorts of differences?
Yes, we do run different scenarios with and without seagrasses. We've done that for many areas around the world. And what we do when we run those models, we can either input in the model, idealize seagrasses distribution. So we could see, okay, let's see what happens if I do add a certain seagrass patch in this area, because that's an area where I really want to add that intervention. Or we could use existing seagrass distribution. For instance, we've had some instances where we had seagrass maps over the years. In some places there was some decline, so we could see how in time a certain decline of seagrasses, what it did to the environment. And what we found is that overall there are direct impacts on the hydrodynamic, which means that the direct impact on, let's say you dissipate a bit of waves. If waves go over a vegetated surface, they tend to become a bit smaller once they go on the other side. But there are also longer-term impact, again, in connection to sediments redistribution, because these environments tend to trap sediments, which again, it can be helpful for our coastlines. And what's important is that these effects can be very spatially variables. So that's why sometimes we have to do models for many different areas, because things will change from one place to another. So we need to check that. And modeling are helpful for that because they are relatively inexpensive to run.
But do your models suggest that we have time for these sorts of natural interventions to get established? Because building a seawall takes time but can be done relatively quickly. Establishing things like salt marshes, things like seagrass meadows, that's years in the making for nature. Do we have time?
I think in some cases we do have time, yes.
Nicoletta Leonardi, she's at the University of Liverpool. But time is, unfortunately, something we've run out of in this episode. That is it for today. But do join us on Friday, though, for the latest look at what is hot in the world of science news, including a rapid way to diagnose and treat bacterial infections. Stay tuned for that. You can, of course, keep up with what we're up to via LinkedIn and Instagram. We're at Naked Scientists on X, and my email address if you'd like to drop us a line about the programme or with any thoughts, questions, feedback or ideas for future programme topics you'd like us to look into, it's chris@thenakedscientist.com. Indeed, I'm Chris Smith. Thank you for listening, and from all of us here at the Naked Scientist team, until next time, goodbye.